Welcome back, and we reviewed complex numbers in the first video. Now we're going to continue the discussion about how this is going to manifest in linear algebra. And so today we've kind of said, okay, we can have complex eigenstuff, and the definitions work similar. So today what we really want to focus on is dynamical systems. Dynamical systems with complex eigenstuff, okay, eigenvectors, eigenvalues, blah, blah, blah. And then the other thing we want to look at is this idea of stability, okay? And we'll get to that in the very last video, okay? But before we go too far down the rabbit hole, let's just do a little bit of warm-up and find the eigenvalues and eigenspaces for this matrix. So I'm going to have you pause the video and find them and resume when you're ready. And here's what I got. So eigenvalues of plus and minus I, and then when I go and find the eigenvectors, same sort of process as before. I end up with I1 and minus I1, okay, corresponding to eigenvalues I and minus I respectively. So, okay, what do we do now? Well, we're done, right? We've answered the question, but can we notice anything that's kind of interesting? So we know that complex numbers come in pairs, right? There's always z and z bar. Well, it just so happens that I minus I is the complex conjugate of I and vice versa. So these two are complex conjugates, and if we look at their associated eigenvectors, those are complex conjugates too. Oh, so it's sufficient to find one complex number, and well, then you get the complex conjugate for the second. Okay, and that's exactly what this next theorem says. If we have a complex eigenvalue of a plus bi with associated eigenvector v plus iw, then we say the complex conjugate is also an eigenvector and an eigenvalue. Okay, so I do want to take some time and prove this in class, which is the video, just so you can see this. So formally, we're going to say let f of a lambda be a polynomial with real valued coefficients okay, and so again, this is really the characteristic polynomial of matrix A. Okay, then from here, what we want to say is if lambda is equal to a plus bi is a root. Okay, and before we can go on any further, we want to just say, why is this true? Well, fundamental theorem of algebra. Fundamental theorem of algebra. Where we say that a polynomial of degree n has n roots, some of which are or may be complex. Okay, but anyway, if this is a root, then lambda is equal to a minus bi is a root. Okay, and so if now we look at the eigenvector, so that's proving the complex eigenvalue is the complex eigenvalue and its conjugate are eigenvalues for this matrix. And now if we look at the associated eigenvector, so this would be a of v plus iw, and we have to remember the definition of eigenvector and eigenvalue. So a plus that is a plus bi times v plus iw. Okay, this is the definition, right? Then what I can do is I can apply the complex conjugate, or I can do the conjugate of both sides. So this would be a v plus iw is equal to, and then bar of a plus bi v plus iw. Okay. And the left-hand side just becomes AV minus IW, because the matrix A already has, or is already real valued. We don't have to worry about that at all. Okay, so just take the complex conjugate of the vector, and now on the right side that becomes a little bit more interesting. It does happen that if you have two complex numbers multiplied together and you take their complex conjugate of the product, you can do the complex conjugate of each individual component. So a plus bi conjugate of that times conjugate of v plus iw. And so this is going to equal a minus bi times v minus iw. And I need parentheses. Okay, and so this fits our definition of having the eigenvalue here and then the eigenvector on both sides. That fits that a v is equal to lambda v type definition. Okay, so that's just a little bit of an overview of we can find eigenvalues and eigenvectors for a matrix that have complex values in them, and then also make use of this other theorem that if we have one complex eigenvalue, we can eigenvalue and eigenvector, we can find another one just using the complex conjugate.